tree says if you observe these things, this is what we expect to see. So to build this particular one, we first noted that color is the most predictive of shape, followed by number. That's just why those appear in that order. And then if we look at the far left-hand cell, when we observe red and the number 0, in every single one of our test cases, it was a square. So we're going to say put 100% for square in that particular one. A more complicated one is over here. If we see purple and 0, we saw 4 times that it was a circle, 2 times that it was a square. So we'll just put in 2/3 and 1/3 respectively. So that was the decision tree for shape. We build a similar one that tries to predict the color, and then one more that tries to predict the number. Although in this case there was nothing that was particularly predictive of number, so the profiling software just returned this brain-dead sort of decision tree. Now let's look at an example at runtime. So all of this previous stuff was done offline ahead of time. Now the system has been turned on. We observe this new query that comes in that's a red square with a 0. So we first look at the color because we want to predict the shape. We see that it's red and we see that the number is 0, so we predict that it should be a square. We see that the shape is a square, so we predict that the color is most likely red, but it might also be purple. And finally, we don't have much of a guess for 0, but we'll throw in our 53. If we take just the average of those three, we get 76%. We'll call that high enough. I'll get into a little bit later how we decide what's high enough, but we'll classify this one as legitimate because it looked pretty good. Now we'll look at the green square with the 1. Walk through a similar sort of pattern here. We see that it's green. We see that it's the number 1. We predict that it should be a circle, and it's not. We look at the shape. We see that it's a square. It should be red or maybe purple, but certainly not green. And then we see the number 1. So we average these together. We get a pretty small number. So we'll say, this one's garbage. We're going to reject this query. Then the last one that we have is this red square with the 1. So walking through that one as well. We're not exactly sure what shape it should be, but a square is pretty plausible. When we try to predict the color, red's a good number. Try to predict the number. We get an average that's kind of in between because this is not quite as common as that first example that we looked at. So there's actually some gray area in the middle where we're not really quite sure whether it's legitimate or not. To relate this back to, here we go, there's the name, Camera, Terzi, and Bertino. This is the most similar related work. In this one they were looking at the SQL that was coming in. The features that they were extracting were which relations were appearing in the from clause, which attributes were in the where clause, and which attributes were in the select clause. So it's a subset of the features that we're looking at. For their prediction phase, what they were looking at, in the presence of roles in the database for the security system, you start with the role and you use the role to predict all of the remaining features, and you're basically measuring the distance, because in this case we're just looking at you count the relations, count how many things were in the select clause, etc. Nice, well-formed numbers, distance metrics make perfect sense. In the absence of roles in the database system, it gets a little dicier. The first thing you have to do is predict a role based on the features you've observed, then turn right back around and say, okay, this is the closest one that matches, but how far are we away from it by going through the same beginning step? And this gives them a pretty good ability to identify anomalous behavior. But once we add in all of the extra features from the query optimizer, we can get that next step. So let me justify that what we're doing is on the right track in terms of our experimental results. So first, the setup for the experimental phase. We obtained a copy of the internal time reporting system. So it was actual internal data from the Oracle system. To construct the legitimate workload, we got a copy of 28 days worth of normal employee activity. So logging in to look at their time card, update their time card, etc. We just looked at the actual select statements. We didn't worry about the updates yet. And then we created 1 year's worth of the daily and weekly reports that are processed for all of the various budgeting people who have to figure that stuff out. In terms of synthetic attacks, what we did was we have all of those legitimate feature vectors. We randomly create feature vectors by sampling from the observed distribution of values. We looked only at the observed values because if we look at all possible values, many of the features we create will inadvertently touch stuff we've never seen before, and it would automatically get flagged as an anomaly. That would make us look a little too good, so we wanted only to focus on the values that we actually observed in the legitimate feature space. And what this synthetic attack workload really does is it doesn't prove that our system is going to stop attacks in the wild. what it shows is, are we creating really good patterns? Are we creating patterns such that if you pick a random point in this high dimensional space, just randomly create this feature vector, are you more likely or not to land by chance in something we've classified as legitimate, or will you end up in hopefully a vast sea of stuff that we flag as not legitimate? The next thing that we did after we put together our synthetic attack scenario was look at some real attacks. So I assembled a security team, and they generated a list of 8 possible goals that an adversary might have if they were trying to attack this system. So the adversary's goal might be something along the lines of, look for employees who are likely to be recruitable. And those employees might be people who have a lot of foreign travel, who look at their time card at odd hours, who work a lot of weekends in the office, things like that. Another goal might be to see if we can get the passwords out of the system, just like I did with the earlier SQL injection attempt. Once we knew what the adversary's goals were, we then asked the SQL experts on the security team, okay, come up with plans. What query would you try to run in order to accomplish those goals? So we mapped each one of those goals into at least 3 different SQL attempts, either downloading all of the data that you wanted in one query, maybe trying to sneak out a record or 2 at a time, in a bunch of little queries, different ways that you could accomplish the same thing by doing some post-processing by the adversary. And then those 8 goals ended up being 33 different SQL injection attacks. I'd like to say that we had the time and money to develop even more, but each one of these attacks is a fair amount of effort in order to actually put together, which is why we needed to back this up with some synthetic results as well to get a feel for the space. So first thing we looked at is performance. If this adds a huge amount of overhead, nobody's going to touch it. So in terms of the performance time measured in milliseconds, if you just run without any of our stuff plugged in, the query optimization task takes about 770 or so microseconds, just under a millisecond, for each query to run. In our case, we built the profiler actually inside some Java code relying on open source stats packages. As a result, there's some inter-process communication because we're using the Postgres system, which is written in C, so our C code had to go out and invoke this Java code. So there's some inter-process communication that happens. That costs you about another millisecond. And then there's the actual work done by the profiler to test the query, and that runs in about 50 microseconds. So in terms of could you deploy this in the real world, if you re-implement the stats, the piece of the stats package that we're using inside C code directly, your overhead's going to be another 50 or so microseconds. I think that's entirely reasonable. If, however, you need to rely on a separate machine, you don't have access to the source code because you're using Oracle or SQL Server, you're going to get this inter-process communication overhead, and it's going to roughly double the time for optimization. So that's probably that threshold where you have to think seriously about whether or not this extra overhead is worth it in your organization if you're running, if you have the hardware only to run what you're your normal workloads. Then in terms of precision and recall, how well are we doing on these synthetic attacks that I described earlier? So what we've got is the top line in blue is a description of, or the legitimacy score assigned to all of the synthetic attacks. And so the closer to the bottom it is the higher the legitimacy score. So a score of 100 says, this thing looks just like we predicted. We got every single feature nailed spot on. And a legitimacy score of 0 says we couldn't identify anything. It's completely anomalous.
What's the x-axis?
The x-axis is simply sorted in increasing legitimacy score, just to give us a smooth curve. The x-axis has no meaning, which is why there's no label on the x-axis. And what this shows is that there's a pretty wide range between the synthetic workload and the legitimate query workload. So we're getting a pretty good discrepancy between the two. I mentioned earlier that I would tell you how we pick a reasonable score. So what we did, I kind of lied when I talked about how we build a cross-feature analysis. In addition to a training and a testing phase, there's actually a tuning phase in the middle. So we do the training, but we hold out some of the data in order to tune the parameters. And the parameter that we care about here is what is that number that we're going to assign as being high enough in order to let the query run. And to figure that out, we then run some of the held back examples through, and we pick the threshold that gives us the optimal F score, the average or weighting of precision and recall. So in this particular case, the number 99.25 is the number that came back with the optimal F score. And if we look at those numbers, then our recall is 98.83%, so we're identifying more than 98% of the anomalous blue queries as being illegitimate, and our precision is 99.2%.